All right, so we had our first little introduction to fluids in class today. Talked about density, we talked about buoyancy. Just kind of as a reminder, we remember that density is usually shown by the rho, and that is mass over volume. And then we talked about the force of buoyancy, which I'm going to write over here as well. And the force of buoyancy was the density of the liquid times the volume of the liquid being displaced, or the volume of the item that's submerged in the water, but only the part that's being submerged in the water, and then times the acceleration due to gravity. Okay, as was pointed out in class, that means that the buoyant force is equal to the force of gravity on the water that's been displaced. So we're going to continue this idea. Another term that we use quite often is specific gravity. Okay, now specific gravity is also called the relative density. The reason being is because it's the ratio of the density of the object to the density of water at 4 degrees C. Now, why water at 4 degrees C? I'm sure there's some historical thing there between the physicists and chemists and some argument. That's usually why they decided on the things they decided on. But just know that that's what it is. So what we're going to say is that the specific gravity is equal to the density of our substance divided by the density of the water. Okay? Now, why would we care? What does this matter? I'll give you just a couple of seconds to think about that. All right. So hopefully you kind of thought of the idea, well, why would we care? Well, the reason being is that if we know the specific gravity of an object, if that specific gravity is greater than 1, then it will sink. If the specific gravity is less than 1, then it will float. Now, why is that? Well, if the number on the top is big and water is going to stay as a constant, right? If the number on the top is too big, if it's bigger than this constant, which is the density of water, then I'm going to get a number that is bigger than 1. Now, that means that the object that I'm talking about is more dense than the water, therefore it's going to sink. Okay? If the number on the top is smaller than water, okay, so a very low number there, then I'm going to get a fraction. I'm going to get a number less than 1. And if that's the case, then it's going to float. This is a way of just comparing it very quickly and easily to water and making that understanding. All right? Good. So that's all I think we need here. The next thing we want to talk about is just pressure. What exactly is pressure? Now, some of you may have heard this definition before or learned this definition, that pressure is the ratio of force per unit area perpendicular to the surface area. Okay, or in other words, pressure is equal to the force that is perpendicular to an area divided by area. Now, this has lots of things that we could go into, details that we won't go into right now, but things like if a force is being exerted on a surface at an angle, then you have to figure out the component that is perpendicular to the surface, right? Remember all that stuff with forces and things like that. You have to have the component, which is very similar to friction. Remember with friction, it depended on the normal force. In a way, pressure kind of is just another normal force. It's another force that's acting perpendicular to the surface. It's just a very specific, special one that we like to talk about. Now, why do we even care about pressure? If it's just the force, then why talk about it at all? Well, to kind of illustrate this point, I want you to take your pen or pencil in your hand. Okay, take the end with the eraser, or the back end, the flat end. Okay, and I want you to tap it against your hand as hard as you can without being overly painful. I want you to get a feel for how hard you can hit your hand without causing major pain, all right? Or even a little. I don't want you to be in any pain. So without causing pain, how hard can you hit your hand? All right, now I want you to stop. Now I want you to turn the pencil around, pointing in first. No, don't do it. Don't do it, please. I don't want to get in trouble. Now think about using that same force to hit your hand with the pointy end. Don't do it. Why are you not going to do it, other than because I told you not to and you do everything that I say? Well, it's obvious, right? The pointy end is going to cause damage. Why? The force is the same. So if the force is the same, what's the difference here? Well, the difference is the pressure, right? The force is the same, it's a constant. But the area of the pointy part of my pencil, right? Here's my pencil. Yep, I'm an amazing artist. This area right here at the tip is very, very small. And if that number is small, then when I divide the constant by that small number, pressure is very big. When I use the other end, it doesn't matter that the area is still small, it's bigger than it was there. So this is significantly bigger, and so when I divide the force by a bigger number, I'm going to get a pressure that is small. And that is the significant thing here. This is why we care about pressure, because it gives us a little bit more information about what's happening in a specific point in time. Now, fluid pressure is going to be even more interesting. We're going to talk about a whole lot of things with this, all right? But yeah, so these are details that we'll be able to kind of dig into and understand how this is affecting any given situation. Now, let's go ahead and throw in a mathematical question, right? Just so that we have an example, we can start working with this. We've got a water bed that's laying flat on the floor. The empty bed has a mass of 10 kilograms, all right, when it's just sitting there. The bed itself has dimensions of 2 meters times 2 meters by 30 centimeters. Obviously, the 2 meters by 2 meters is the part that's flat against the ground. So I'll go ahead and draw it for you. Again, I'm really a decent box drawer. Okay, so 2 meters, and 30 centimeters, which I'm going to write as 0.3. It does have two figures there, so I'm going to go ahead and write 0.30. When filled, water has a density of about 1,000 kilograms per meter cubed. Find the pressure of the filled bed on the floor. All right, well, in order to do that, we need to take pressure. So pressure equals force over area. All right, the area, and you're welcome to work ahead on this. I'm just going to go ahead and work through at a slower pace, and if you get to the end, great. You can fast forward through whatever else I had to say on this till you get to the answer. But yeah, go ahead, give it a try. Or pause it and then watch it, whatever you want. So area, of course, is going to be the area that's in contact with the floor, which is this side right here, which is 2, and that side right there. So 2 times 2 is 4. Luckily, it's already in meters, so it's in my SI units. That's going to simplify things for me. And then I've got the force on the top. So the force is going to be the force with which the bed is pushing down on the ground. So that's going to be the force of gravity on the bed, because it's going to push down at the same force the ground is pushing up on it, because it's in equilibrium. It's not accelerating. There's no other forces in play here. So what we're going to need is we're going to need the mass times the gravity. And mass needs to be the mass of the water inside the bed plus the mass of the bed itself. The mass of the bed itself, it told us, was 10 kilograms. The mass of the water, well, to get the mass of the water, we're going to have to use our density formula. The density formula was the mass divided by the volume. So if we take the volume times the density, we get the mass. So the volume of the bed is 2 times 2 times 0.3, which would be 2 times 2 is 4, times 0.3 would be 1.2. That's, if I do it as 0.3 meters, then it's already in meters cubed. I'm actually going to keep track of my units here because I feel that that's going to be significant later. Okay, the density there is 1,000 kilograms per meter cubed. So when I multiply those, the meters cubed are, of course, canceling out, giving me 1,200 kilograms. All right. Now, the 1,200 kilograms is going to go right over here as the mass of the water. So I go 1,200, and I add on the 10 of the actual material of the bed. And then, when I have that, the 1210, then I'm going to multiply that by gravity, which is 9.81. And what I get is 11,870. So I now have 11,870 and I do get a 0.1, but that's not going to be important later. That's in kilograms. Sorry, that was not in kilograms. The mass was in kilograms. Kilograms times gravity, which was meters per second squared. That gives me a force, which is now newtons. And then divide it by the area, which was 4 meters squared. So I divide that by 4, and I get my final answer, which is that the pressure is equal to 2,9, and then I'm going to put this in 3 sig figs, so 2,970 newtons per meter squared. So that's in 3 sig figs. I've rounded it. I put the units down as newtons per meter squared. Now this should make sense because pressure was defined as force over area. And if pressure is defined as force over area, it should be newtons over meters squared. And that is the answer to our question. However, I'd like to touch on that just a little bit more. Can we talk about the units here? Okay. The units for pressure. We know that a lot of times in the SI, sometimes we'll create new names for types of units. Okay, when you learned about force, you learned that the unit for force, even though force was kilogram meter per second squared, you learned that we could summarize that by calling it newtons. Now that made sense. Newton was the guy that did significant work on forces. We learned that energy, force times distance, right? We take all that stuff and multiply it by another meters, and it becomes energy, which we defined as joules. So the type of units that we use for pressure is pascals, okay? Pascals, which is usually written as a PA, okay? It's not a single letter, sorry. This is one of the few times that we actually use PA, pascals. And 1 pascal is equal to 1 Newton per meter squared. And if we go further, we can write this in fundamental units, right? Because we know that a Newton, you can get this from force equals mass times acceleration or something else. But a Newton is kilogram meters per second squared over meter squared, which means that a pascal is kilograms per second squared meter. And so that's our pascals there, right? That's our force, mass times acceleration is force divided by the meter squared. All right, so that's the fundamental units. We call it the Pascal. Other units that you may want to get comfortable with in terms of pressure, ATMs. You may have used that in chemistry, atmospheres. Okay, an atmosphere is approximately 10 to the 5th pascals. Okay, so 100,000 pascals. That makes sense because air pressure at normal conditions at sea level is generally pretty close to 100,000 pascals. That's why we say that it's 1 atmosphere. It's about 1 atmosphere of pressure, what we expect here on the surface of the Earth. You could also use the one that a lot of people are familiar with is PSI, pounds per square inch, right? Which of course makes sense because pounds are force and then per inch squared is per area, all right? You may have to do some conversions with that, or they may just give problems in that in those units. So be comfortable with that just as you work through year 1, dealing with unit conversions and things like that. But these are the ones that are very, very commonly used. There's other things, milligrams mercury and a bunch of other stuff that you will, if you go further in engineering and things like that, you'll talk about those. But for our purposes, pascals, atmospheres, and PSI are plenty for us. All right. So I think that's good for that question. Let's move on to the next one. All right. So 2 points that are important when talking about pressure. Okay. The first point is that pressure is in all directions. Okay, and that's what I'm hoping to show here is that if we give an infinitely small point in this fluid, pressure is on that point in all directions. Okay, now because it's at that point, the pressure is equal in all those directions. Okay, it is always perpendicular to the surface of the object, right? So no matter what the shape of the object is, because it is in all directions, it's always perpendicular to the surface. Okay. The second point that we need to make is that at a given depth, pressure is always the same in all directions. So it doesn't matter whether my guy is here or if it's over here to the right or it's over there to the left. As long as I'm at that same depth, right, then it's going to be the same pressure. Now this is important. This is an important idea. We kind of talked about this in class, that the pressure at this point is due to the water that is directly above it. And it really is just the water that's directly above it. None of the rest of it matters. Okay, none of the rest of the water matters at all. All that matters is the water that's directly above it, or that would be if it were in a straight line. And I'll show you that in just a minute with a couple of concept tests. But those two important points are very significant. Number one, pressure is in all directions. Okay, and number two, that at a given depth, pressure is always the same. Now what that means with a container, and that's why I've got my container over here, is that the pressure or the force will always be perpendicular to the surface of the container. All right, and that's just kind of an important idea, is that the pressure is always going to be perpendicular to all of the walls. Okay, any of these other things aren't part of the pressure, because remember, pressure is dependent on the force that is perpendicular. All right. All right, lovely. We talked about that we use constant density fluids and incompressible fluids so that the density is the same everywhere. So let's go ahead and do our first concept test here, which is to rank the points in order from lowest to highest pressure. So I've got 3 points, A, B, C, and D here. All right, you can see them all, A, B, C, and D. So try to rank those based off of what you see here, the fluid that's on top of it. You got some different shapes, kind of a test tube, a wide test tube, a thin tube, this kind of bulbous thing, and this thing where you got a whole lot of water there that's being swirled up. All right, so go ahead and see if you can rank those from lowest to highest. Pause the video, and after a short pause, I'll go ahead and talk about the answer. All right, so hopefully you've got your ranking done. You may have even done it before I finished talking. But yes, the answer, of course, is it was a trick answer that they're all the same. The pressure is the same in all of these locations. Why? Because the height of the water, you'll notice, is the same in all of these, okay? And because the height of the water is the same in all of these, then therefore, if the height is the same, the pressure must be the same for all of these. Okay, that has to make sense. Okay, think about this. If you dive down, a foot down in the swimming pool, is that more or less pressure than if you dive down in the ocean? Well, it should be the same. The fact that the ocean is much, much wider and there's a lot more water above you isn't going to make a difference. If you're a foot down, you're a foot down. The pressure is the same, assuming, of course, that the pool water and the ocean water have the same density, which I know is a bad assumption because of the salt and chlorine and comparisons and things. But you get the idea. At a specific level, the same depth, as long as you're at the same depth in the fluid, the pressure should be the same. All right. Here, let's try a different one. So here I've got some completely different shapes, right? You can see that number 3, you've got a little bit more water up here. Number 1, there's a little bit less water above. You got even here, and this one kind of bows out. So it looks like you got some extra water here in the middle. So if we consider a point at the bottom of each of these containers, okay, at which of these containers would have the highest pressure here at the bottom of the container? All right, so rank it again from highest to lowest. Go ahead and pause me. All right, well, hopefully you got it, since we literally just talked about it. all of these would have exactly the same height, right? The same height for all 4 of these. And because they're all the same depth under the water, that means they should all have exactly the same pressure. All right? Leads us to the last thing that we're going to talk about here. This is Pascal's Principle, which is why the units, like I talked about, right? Joule and Newton got units named after them because of their significant work in the area. Well, here's Pascal. Pascal, his principle said, any change in pressure it applied to a completely enclosed fluid is transmitted to all parts of the fluid evenly, as well as the enclosing walls. Pressure depends only on depth. Shape of the container does not matter. So there's actually 2 things here, right, that we want to pay attention to. One is what we just got from the 2 concept tests there, that pressure depends only on depth, okay? The second thing I want to make sure that you're noticing too is that when we apply a change, when there's a change in pressure, that change in pressure is transmitted to all parts of the fluid, including the walls, right? Because the walls get the same force as would be inside of the fluid there. All right, so Pascal's principle, make sure to take note of these 2 things. We'll actually start with that in class next time and do some calculations and some other interesting things associated with that. But that's it for today. I just wanted to give you a little bit more background on some of these concepts so that we can go ahead and get started next time. All right, that's it.